This is lesson 7 in the thermal physics topic. It is a lesson on gas laws, the laws of ideal gases. There are a few PAGs to do when we come back to school as well. First of all, to think about the ideal gas laws, we need to think about what the variables of a gas are. Now, by the variables of a gas, I mean how can I describe my gas? Well, first thing I can think about is the volume of my gas. I could think about how much space my gas takes up, and I could change that by changing the size of the box or the container the gas is in. I can think of the temperature of the gas, and I can measure that with a thermometer, and the temperature of the gas tells me the average kinetic energy of the gas particles. In the last lesson we said that each particle will have a different speed, that the speeds are random, but there will be an average speed and therefore an average kinetic energy we can work out, which tells us the temperature. We can measure the pressure of a gas, and the pressure of the gas tells us how much force the gas particles are exerting on the walls of the box. Finally, we can measure the number of molecules of a gas, and you can change that by sort of attaching a pump to it. When you pump up a bicycle tyre, what you're changing is the number of molecules inside it. So you're changing the number of molecules or the mass of the gas inside. Now these are the 4 variables we're going to be looking at and seeing how they relate to each other. For example, if I change this, how does it affect this? Or if I change this, how does it affect this? Etc, etc. Now, when we investigate the relationship between variables, we need to follow the principles of science. We need to have an independent variable, a dependent variable, and a control variable. The independent variable will be the variable that I change, the one I'm changing. The dependent variable will be the one I'm observing, the one I'm measuring. I'm seeing how I change this, what impact does it have on this one? And that means I have to keep the other variables the same. Now, we had 4 variables: volume, temperature, pressure, and number of molecules. So first of all, let's look at what happens when I change the volume and the impact that has on pressure, which means I'm going to keep temperature and the number of molecules the same. So what happens to pressure when you change volume? Let's have a look at our simulation first. So at the moment I've got my box at its full size, and I can see the pressure hovers around 35 atmospheres pressure, which is just another unit instead of pascals. Now I'm going to change the volume, I'm going to decrease the volume, and let's see what happens to this number. So let's decrease the volume, let's half it, and we can see it about doubles the pressure. So as I increase the volume, what happens to the pressure again? The pressure goes down. So there's an inversely proportional relationship. So after looking at that, I can see that as I increase volume, pressure decreases. So or decreasing volume now, if I were to decrease the volume, the pressure would increase. So decrease volume, increase pressure, which means they are inversely proportional. Pressure is inversely proportional to the volume, and I can therefore say that pressure times volume is equal to some constant. I can say that the pressure initially times the volume initially will therefore be equal to the pressure after the change times the volume after the change. P1 V1 is equal to P2 V2, because they would both be equal to the same constant. And in this case, we kept the number of particles and the temperature the same. And you can note down that whenever you do an experiment at a constant temperature, it's called isothermal. So that change was an isothermal change. When I changed the volume, it was an isothermal change, no change in temperature. This is called Boyle's law. And if I plot a graph of pressure against volume, I would get these curves. And you can see the shape of the curves represents the fact that the relationship between P and V is inversely proportional. What do you think the 2 different lines represent? Well, the 2 lines represent the experiment done at 2 different temperatures. Across that whole line A, the temperature never changes. And then at B, it's a new experiment done at a different temperature. But the temperature at all those points will be the same, because we kept that the same. To get a straight line, I would plot P against 1 over V, and then I would have a straight line where the gradient of the line was equal to the constant we saw earlier. Let's try a worked example of this. So I've got some gas now occupying a volume of 4 times 10 to the minus 3 meters cubed, and it exerts a pressure of 90 kilopascals. What is the pressure when I halve the volume? So I know the equation is P1 V1 equals P2 V2. My P1, my initial pressure, is 90 kilopascals times 10 to the power of 3. My initial volume is 4 times 10 to the minus 3. My second volume, after the change, V2, is half of that. So it's going to be 2.0 times 10 to the minus 3 meters cubed. Oh, sorry, I don't know why I put a minus there. That shouldn't be minus. And P2 equals, well, that's what I'm looking for. So I'm going to rearrange this equation to get it as P2 equals, and I would get that. P2 equals P1, V1 over V2. I substitute in all of the values that I know here, and I would get 180,000 pascals, or 180 kilopascals. Pause the video now and try these questions after we looked at that worked example. I'll show the answers in a second. And here are the answers to question 1 and the answer to question 2. The next change we're going to look at is what happens to pressure when I change temperature. So this time I'm going to keep volume the same and the number of molecules the same. I'm going to change temperature and see what happens to pressure. Let's have a look at the simulation again. So here I've got my box. I'm going to keep volume the same. I'm not going to allow the volume to change. And what I'm going to do is I'm going to heat up the box. I'm going to change the temperature and see what happens to the pressure. When the temperature is 305 Kelvin, the pressure is around about 40. So let's heat it up now. So let's heat it up all the way to 450 Kelvin about. So about 450 Kelvin. And we see the pressure has increased now up to 59. And you can see as I keep on heating, you can see that pressure just keeps on increasing. And as I cool it down, the pressure decreases and decreases and decreases. So in that experiment, we saw that as you heat up the gas, as you increase the temperature, particles move around more quickly, and you increase the pressure. That is sort of expected. And what we did is we kept volume and mass constant in that case. And we saw that decreasing the temperature would decrease the pressure, or increasing the temperature would increase the pressure. So pressure and temperature are directly proportional to each other. We can rearrange that and introduce an equals constant, so we get P over T equals a constant. That means that P1 over T1 would equal P2 over T2, where this is before the change and this is after the change. For this to work, temperature must be in Kelvin. If you don't have temperature in Kelvin, this will not work. So do not forget to change degrees Celsius into Kelvin here. Let's have a look at an example of this. So I've got some gas exerting a pressure of 50 kilopascals when it's at a temperature of 233 Kelvin. What is the pressure when the temperature is raised to 749 Kelvin? Well, initially my pressure is 50 kilopascals, 50 times 10 to the power of 3. And my temperature is 233 Kelvin. After the change, so after I increase the temperature, my pressure is what I want to work out, and my new temperature is 749 Kelvin. The equation was P1 over T1 equals P2 over T2, and I'm going to rearrange that to get it as P2 equals, so P2 equals P1 T2 over T1. Substitute in all my values, and I get comes to about 1.6 kilopascals. Oh, sorry, I think I've got that wrong there. That should be 16 kilopascals. That's my mistake. That should be 16 kilopascals. So ignore that decimal there. It should be 16 kilopascals. That should be the value. These are some questions, so pause the video now and try these. And these are the answers to those questions. If we plot a graph of pressure against temperature, we see something quite interesting. What we see is that pressure would become 0. If I extrapolate my line of best fit down here, I can see that pressure would become 0 at some temperature. So where it crosses the x-axis, that's when pressure is 0. The temperature that it crosses the x-axis at is absolute 0. This graph is plotted with degrees Celsius as the x-axis, but if I plotted it in units of Kelvin, it would cross through the origin. Because when I reach absolute 0, which is 0 degrees Kelvin, then I would have 0 pressure. So this is a really useful way that you can actually try and estimate absolute 0, and it's a practical we're going to do back at school. The final equation we're going to look at is the equation of state of an ideal gas. This is the sort of main equation. And sort of combining what we've looked at so far, we can get PV over T equals constant. And we can plot PV, which is pressure times volume, against temperature, and we get some straight lines. And actually what we find is that the gradient of those straight lines is equal to nR. N is the number of moles. You might remember that from the last lesson. N is the number of moles, and R is something called the molar gas constant. So N is the number of moles, R is the molar gas constant, and it's just a number, it's a constant number, and it's equal to 8.31 with the units of this. So that brings the equation to actually be this. This is our equation of state of an ideal gas. It's PV equals nRT. P is pressure, small p, capital V is volume, N is number of moles, R is the molar gas constant, it's 8.31, and T is temperature. And this must be in Kelvin. This is in pascals, this is in meters cubed, this is number of moles, this is 8.31, and this is temperature, must be in Kelvin. A reminder. And we can actually say that if N is constant, so if I don't change the number of moles, then I can actually say that P1V1 over T1 is equal to P2V2 over T2, which is a slightly more complicated relationship than the ones we were looking at before, where we only keep one constant. Let's try this as a worked example now. So let's say I've got 3.5 meters cubed of gas, pressurized gas, should say gas there, and it contains 425 moles of a gas. So I've got 425 moles of a gas, takes up that much volume, and it's at that temperature. Calculate the pressure of the gas inside the container. Okay. So I've got a volume of 3.5 meters cubed. I've got N, a number of moles of 425, and I've got a temperature of 25 degrees Celsius. But remember, I've got to change that to Kelvin. So I'm going to add on 273 to convert it, and I would get 298 Kelvin as my T, my temperature. The pressure is what I want to know. So my P is the number I'm looking for. The equation is PV equals nRT. I'm going to rearrange that to get it as P equals, which is what I want to know, and I would get nRT over V. I'm going to substitute my values in, so V, N, and T, remembering that R is 8.31, substituting in my values, and I get an answer of 3.01 times 10 to the power of 5 pascals, or 301 kilopascals. Let's try some multiple choice questions now. So read the question and see if you can get an answer. We'll go through it in a second. Okay, so what you should have recognised was that N is a constant. Because it's a fixed mass, N is a constant. The number of moles is not changing. Which means that according to the equation of state of an ideal gas, if I rearrange this to get P, because I'm looking to see how pressure changes, I would get nRT over V, but now N and R are both constants. N and R are both constants, which means that pressure is directly proportional to T over V. The combination of these that would result in doubling the pressure is B. Because if the volume changes to the volume over 4, that's like quadrupling the pressure. That's like the pressure being times by 4. But if the temperature halves, then the pressure would half of that. So I multiplied it by 4, but then I halved it, so that would give me double the pressure. Finally, pause the video and read the question and give it a go. Okay, what you should do to answer this is you should recognise that if I've got some gas exerting some pressure and P is at a lower temperature than Q is, I must have more particles for P than for Q. I do it as a ratio of the temperature of P divided by the temperature of Q, and it's 0.8 times the number of molecules in Q.